Then we also can open an Excel spreadsheet and save it somewhere. Because we want to compare kind of results. So then we're going to treat the first case. So first case, we basically want to simulate like a 2 meter long vertical soil column. Initial condition is pressure head of minus 100 centimeters everywhere. So like one, whatever you want to do. So the initial condition is I see it's minus 100 centimeters. Pressure for this material. Then top boundary, so boundary condition top is constant pressure head of 0 centimeters. Then boundary condition on the bottom. Then we can copy this. In each case, we got to do this free drainage. With the only problem with hydrus, it's in Excel actually to make it. So, and then it also says, when you look at the very top, it basically says that we want to kind of run our model for 24 hours, and we want to have an output every hour. So every hour we should get the result. Then we also want to kind of insert observation nodes in the profile. So that we know what exactly happens to the soil parameters at those depths, moisture. We're going to insert one node at 26 centimeters, and the next one is 50 centimeters below the surface. I'll show you how to do this. And then we always want to compare, so we go through kind of a series of iterations. And whenever we have a type 1 top boundary condition, basically we want to plot the surface fluxes for those two cases we compare. Whenever we have a type 2, so imposed flux, we want to kind of plot the pressure distribution of the surface. And then we always want to kind of compare what happens to the water content in 26 and then 50 centimeter depths. This is basically the problem statement. So let's start with the first one. And so when you open hydrus, basically you want to specify a new project. File new. And I would like P1 stands for, or P01 stands for problem 1. We don't really need to add any description. And then I want to put this into my folder on my desktop. So this is where I want to put all my results into. And you, of course, have something else specified in your desktop. So this is basically P01 refers to the first problem there. Okay. So mind processes. Initially, we really only want to deal with water flow. So don't want to check anything else. Then we go to next. We want to specify our kind of length units in centimeters. The depth of our soil profile is 2 meters, so we need to put in 200 centimeters. Number of soil materials, so it's a uniform profile, so we only have one material, loam. We don't have any layers, and we want to model vertical flow, so there is no decline. So there is one, so everything should be alright. Then we want to use hours. And we say we want to model over 24 hours. So that's fine. We don't specify any time varying boundary conditions just yet, so we'll do this a little bit later. So time is in hours, final time is 24 hours. Next. Now, since we want to have a result every hour, we want to print 24 times. So now basically the print times every one after 2 after 3. Hopefully they'll go all the way up to 24 hours. Okay. We don't really change anything with those iteration criteria, so we leave this unchanged. We'll do next. Then we really want to do the very simple case. We use genug Noirem with no hysteresis. So next. And then we say we take like the simplest soil. Happens to be loam, so this usually everything works with loam. Or maybe not, let's see a little bit later. So we choose loam, we choose next. Then we want to specify a constant pressure head on the top. This is our top boundary condition. Free drainage at the bottom. And then we want to specify the initial conditions in terms of pressure head. So we go next. Then it asks us if we want to run a profile application. We say yes. Yes, we want to save this. Before we do this, I only want to quickly show how we actually can change the spatial discretization like we just mentioned. So profile discretization. First of all, simplest way is I only change the number of nodes. So now I have 2 centimeter layers. If we change this to 201, of course the discretization gets much fewer. So now we have 1 centimeter layers. This is actually not related to the problem, it's only a small extension to what they showed on the PowerPoint. But let's go back to default. So now in case I would have like a layer somewhere in between, I would insert like a fixed node. Let's say we put this in 100 centimeter depth. So when you look at your bottom right corner, you see actually the elevation. So put one of those nodes fixed this depth, and then I basically want to change the density. So I push density, and I mark exactly this interface. And then I actually can change this, let's say to the smallest. I think the smallest is 0.001. Only insert fixed, so you only insert like a location into the profile. I'll show this again.
You said 100 something?
At 100.
Only you can do this wherever. Let's say we have like a layer, 1 meter layer of sand on top of 1 meter layer of clay. So we know that the interface is exactly at 100 centimeter depth. And then when you look at your right bottom corner, this actually, when you move through the profile, this gives you the elevation. This is exactly how you can choose the point. So when you look at this one here. So I go back before the. So I insert like the fixed location. Then when you move down here, you see actually how the elevation changes in the bottom right corner. Once you reach like 100 centimeters, this is where I know my interface, hypothetical interface, now we only have one material, but let's assume there were two. Would be, so I would insert a fixed location here. And then I go to density, and I basically click on this fixed location, and then unmark this, and then it basically would increase the discretization 0.001 upper and 0.001 lower, and you would say okay. So now you see exactly the interface. You have a much kind of denser spatial discretization. You could, for example, if you have some concerns or that something isn't working well with the upper boundary, you again can insert some fixed location and then say density. Now we actually want to have a denser discretization close to the surface, so we push the surface node, and then I put this to 0.001. Then it basically changes this, so now you have better discretization here, up to here, and then you have really dense. So this is actually the first step. If it's not converging, you can change the discretization. Before inserting those fixed nodes, it's always in 1D, you can change the layer density. So you can do this, if you want to do this for half a centimeter, you go to 401 or so.
What is this telling the system to do, like changing that density?
No, the spatial discretization now we have, when you have very kind of high gradients, you want to have your spatial domain, so you want to have many layers close to those interfaces, so that this transition is a little bit smoother.
Taking place. Okay.
So this is the idea behind this. So what you really do, you either kind of change discretization of the spatial domain, make it smaller. The first thing what I would do, so we can go default, we can go, as I mentioned, 1D doesn't really make any difference. We change the number. We go to like 401, this would mean we have like 5 centimeter increments. So now we have like so each, so you have one simulation node each half a centimeter. And when we had it before, we had like every 2 centimeters. And for 1D, this doesn't really change anything with computational time. But if you do something like this, it's really where you have like a complex, three-dimensional kind of node kind of mesh, then it kind of exponentially increases the computational time required to solve the problem. But in some cases, you might not even do this. You can go back to this. Let's say default. And really, when you know your interface is at 1 centimeter depth, now we insert, and you know there might be some issues because we have coarse over fine or fine over coarse. We only insert like the location.
So if you were gonna model a 2-layer or multiple layer, you would automatically do this?
No, not automatically. If it's running without it,
Okay.
all those things, you don't want to complicate this stuff. You only want to do those things if you're running the programs.
Okay.
So if for some reason you don't get the result and you have some error message that the calculation is not converging, then you kind of do those things. And then you can change that. I think 0.001 in terms of centimeters is the smallest one you can go. So now you know at the interface you have a lot of nodes. Let's go back to the board. Let's go back to our board. This was a small like excursion into something we talked about before. So we basically leave this profile discretization material distribution. We only have one material, we have none, so we don't need to change this. Scaling, we are not dealing with scaling of hydraulic properties. We need to, of course, specify our initial conditions. And it happens to be that it's already there. So we said we are going to start with minus 100 centimeter of pressure head. Does anybody understand what this actually means in terms of moisture? So you always need to keep the soil water characteristic in mind. So basically now the moisture content throughout the soil profile would be equivalent to a metric potential of minus 100 centimeters when we look at the soil water characteristic. We would kind of know the moisture content. But as we mentioned, it's always better to kind of specify the pressure head instead of the moisture content. So we do this, so everything is fine. Then we want to kind of insert observation points. So we said we want to have 1 point in 26 centimeters, so I want to insert. Then again, you follow it on the bottom right corner. So you go down until you hit 26 centimeters. And then you click once. So now basically we get an output, an additional output for exactly this step. Then we want to insert another observation point in 50 centimeters, so we go a little bit further down. 50 centimeters, and now we have 2 observation nodes. Basically, whatever we simulate, we get the result for 26 centimeter depth, and we get the result for 50 centimeter depth besides everything else. And the only thing you need to do, once you're done, you need to press escape to get out of this window. Then we basically avoid the discretization time that we can do in this visual module. Then we only close it. And then it asks us, you want to save changes? We say yes. And already, since we didn't simulate run it before, we say okay. Oh, then we need to go back one more time. Let's say okay for now, because we forgot something. We actually said that we want to impose 0 pressure head at the top boundary. So we actually need to go back to the gravigator, go back to the initial conditions, pressure water content, edit condition. Then we need to go to the very, very top, so the surface. We push this one, and here we put 0. This is actually how you, for this one case, how you input like constant pressure boundary conditions. So if we would have like bonding 5 centimeter, we put 5 centimeter. But we have 0 bonding, which actually will generate, so because the soil is initially dry, it actually generates some influx. So we say okay, and now you basically see everything but the surface is at minus 100, and then the very surface we have 0.
Can you repeat that?
So let's go edit conditions. Let's do this. I go back like we did before, so I use this is how we had it before. So we said it's uniform throughout the soil profile, minus 100 centimeters. Then we only go back in, we go edit condition, and then we go to the very, very top of the surface. Double click, and then we basically only want to change this value to 0. This is basically our constant head top boundary. We say OK. And now you see it's basically 0 on the top, and everything else is at minus 100 centimeters. Then we can go out. So it changes, yes. Okay. Then, we can look at the profile summary.
We gotta execute first.
No, this is, we can look at this. This is basically only what we kind of graphically input. So now you see the discretization, so 2 centimeter layers. Top layer we have 0 pressure, swell. The other remaining profile we have minus 100 centimeter. We don't deal with root water uptake, we are not dealing with scaling, we have one material all the way down. And we don't have different layers. So we only put okay, and then we only calculate, we only want to execute hydrus. You see okay. Of course this goes very fast, absolutely no problem. And then we press enter. So now we have our first result. And the easiest way is really to put this into Excel. So if you go now to our Excel spreadsheet, we want to open, file open. Now I have this on my desktop. Homework 3, so problem 01. Oops. Oh, that's the reason. I need to all files. So now we have different files. And we said that we basically, when we look at the instructions, so we want to kind of look at the water content at 26 and 50 centimeter depth and how it progresses with time. And there is a file that is called observation node out, OBS node out. This is, for example, if you have 10 observation nodes, this is where you would see all this information. And then we're going to open this one. And then again, we say delimited, space, finish. And then what you see, node 14, so this basically 26 is 14, it's 14 nodes below the surface, it's 26 centimeter. So we have the time, so this is what we want to copy. To our master spreadsheet. So we put this here. Right, 26 centimeter.
How did you get it to not copying the single cells?
Oh, to mark everything? How did I do what?
Never mind, disregard.
Time, and then we have, we also want to report the volumetric water from there. And then we have another one for 50 centimeters, or this is the other node. Also volumetric water from there. This one, basically we can mark actually. This one, if you are very familiar with Excel, actually do this once. Only press the control button, the first one, click the shift button, click enter, so now we can basically copy both of them together. Oh, the copy is time. Yes, so this is our volumetric water content. time steps, they're actually really determined by hydrus. So for different soil types, for different boundary conditions, you actually see different kind of time steps, because hydrus optimizes the time step to reach a solution. And then we also said we want to actually, when we go this, so we have now a type 1 boundary condition, so we want to get the surface boundary flux. Fine. So to get this one, we actually need to open the T-level file. Again, we want to have like this would be surface flux. And to get the surface flux, we need to open the T-level file. Open. We go back to this one. T-level out. Time actually should be the same, but our portion we copy it again. And then we need to find the surface flux. So this is the sum. We can either kind of use the cumulative one, or we can plot the actual one. Let's plot the actual surface flux. So time. Then we quickly want to plot this. So we want to plot what happens with the moisture in 26 and 20 and 50 centimeter depths.
Alright, so I'm just catching up real quick, but what were those last two columns that you have right there? That's from the T out file.
This is only the surface flux.
Surface.
V top.
V top for both 26 and 50.
So you only need to look at the instructions and find the right the right thing in the T-level file. So that is a graph now. So we basically simulate over 24 hours. Series 1. series 1, this would be 26 centimeter depth. Since this is our first, probably we want to compare it with other ones that probably look like P1 bracket. And then I do, so the second series, this is for 50 centimeter depth. And also like problem 1. So now when we look at this, what does this really tell us? Maybe let's plot the surface flux first. So again, let's make a plot. I think if we do this. So, what does this really tell us? I have initially a not a very dry, kind of partially dry soil profile. Then I basically have zero pressure head on the top, so actually water is flowing into the profile. So negative flux means flux into the profile until it basically saturates the surface. Then you basically have like zero flux on top. A flux of -1 on top. This basically, so initially the soil is very dry until it reaches a certain wetness. The pressure head is not kind of high enough anymore to wet it completely up, zero. So it basically remains at -1. And then when we look at the moisture distribution, what does this tell us? So basically it only tells us we start with the same initial conditions. So 0.25 volumetric water content is basically the water content equivalent to a matrix potential of -100 centimeters. Then as water actually infiltrates, you basically see that it reaches the first node for 26 centimeters, of course, first. Then it starts going up until it's getting until it's equivalent to a kind of flux of -1 or ahead of 0. So this is saturation. And then you basically see what happens in 50 centimeter depth. Of course, the water takes much longer to reach 50 centimeter depth, so there is a time delay, and then it also goes up. When we go back to hydrus,
is that surface flux of -1, and that's just the maximum infiltration right there?
this is basically because the soil properties, there is actually more water taken up than we apply. So that's the reason it stabilizes.
More water taken up than is applied.
So that's the reason it goes not really